Hello, my name is Tomasz Drab and I will present a joint work with Małgorzata Biernacka, Dariusz Biernacki and Witold Haratonik titled An Abstract Machine for Strong Call-by-Value. We can say that this phrase made up a goal of this paper, so we will start with motivation for strong call-by-value and the same for abstract machines. Then I will show a short example of functional correspondence as a tool of constructing abstract machines. Then we'll have an overview of our derived machine, and we'll finish with its formal connection with strong call-by-value operational semantics. We will consider lambda calculus as a programming language, but in lambda calculus there are many ways to simplify an expression. For example, we can substitute an unreduced expression, and this approach is called call by name. But we could also simplify the argument first, and as soon as it is an abstraction, then we can substitute it. And this approach is called call by value. And this way we've obtained an abstraction again, so in so-called weak reductions it's a normal form because they don't go with reduction under the lambda. So to proceed with radices under the lambdas, we need to turn to strong reductions. And strong call-by-value should be just a strong extension of weak call-by-value. And why strong call-by-value? First of all, strong call-by-value normal forms are full normal forms, and this full normalization can be used in proof assistance such as CoC during the type checking. Call-by-value itself is widely applied and studied, maybe because it avoids recomputation of arguments at the strategy level, but it also supports recursion, which is not the case in leftmost innermost strategy. And what an abstract machine should be? With this picture of a Turing machine, I would like to give an intuition that an abstract machine should be a finite state machine working on unbounded data, but only data, not higher order functions or other entities acting non-locally. And as an example of an abstract machine for a functional language, I will shortly show a well-known Crégut machine. The data it operates on are terms in the Brown notation, which means that variables identify their binders by the number of other binders between them, so the names next to lambda are not needed. On closures, which are pairs of terms and environments, where environments and stacks are just lists of closures. And finally, the main data structure is configuration, which is modified by finite set of transition rules. And to start call-by-name reduction of a term t, we put it into a configuration with empty environment and empty stack. Then we pattern match on term, and to proceed with application, we put it right-hand side on the stack of arguments. If it's an abstraction, we take an argument and extend an environment with it. And if it's a variable, we take an appropriate entry from the environment. And why abstract machines? The first reason is that they give a straightforward implementation guidelines. And this implementation is in trampoline style, which means we can run it for a given number of steps, resume it later, or interleave with other computations. And from theoretical point of view, it's an operational semantics, and more detailed than small step semantics, so we call it microsteps operational semantics. And together with this trampoline style, it is a didactic value, because students can run an abstract computation step by step on their computers. And finally, abstract machines give a cost model for time complexity by just number of computation steps. And if this machine is really a finite state machine, this cost model is quite realistic because a computation step can be done in constant time. So we would like to construct an abstract machine, but doing it by hand is quite hard and error-prone. So we would like to have a more systematic approach, and we will use the functional correspondence between evaluators and abstract machines to construct one. And we'll see an example in Occam how it works. We will use again syntax of lambda terms in the Brown notation, which will be common for some next slides. We'll start with defining a call-by-name evaluator. So we define values, which wraps functions taking thanks as an argument, and thank is just a computation that may return a value. Here we have an auxiliary function unwrapping a value to behave just as function, and auxiliary data type of environment, which is just a list of thanks. And to evaluate a term in given environment, we pattern match on term, and if it's a variable, we take again an appropriate entry from the environment. If it's an application, we evaluate left-hand side and apply it to thank, evaluating the right-hand side. And if it's a lambda abstraction, we return a value wrapping a function which evaluates its body in extended environment. But if term is closed, we can evaluate it in empty environment. But this evaluator is not an abstract machine. It contains two higher order functions, which we can defunctionalize, and they are turned into data which are interpreted by first order functions as functions in places where they were called. But still, this evaluator is not an abstract machine because it contains a non-tail recursive call of function eval, which would behave non-locally. So we make a CPS translation of this evaluator, introducing a higher order function, so we defunctionalize again. And this form, after some rewriting and introducing a configuration type, gives us something very similar to what we've seen before. This way, we've derived an abstract machine for call by name, namely the Crégut machine. And the path of our paper is the following. We start with Crégut's KN machine, which stands for Crégut normalizing, and we deconstruct it because the process we've seen is reversible, and we get an evaluator with normalization-by-evaluation, and similar deconstruction was done also by Munk earlier. Then we modified slightly this NBE, and we obtained an NBA akin to Filinski and Rohde NBE. And then we've constructed a machine named KNV. A word about modification of NBE. After the construction of Crégut's KN machine, we've got these types, and abstraction were taking thanks as arguments. So we modified it slightly to make abstractions taking values as arguments, hoping that it will lead us to call by value. And let's take a look at obtained machine. It operates again on lambda terms in the Brown notation. It has environments with a bit more complex values, and there are many types of stack elements. And finally, there are 3 types on configuration. There are 4 rules similar to rules of Crégut machine, and 9 other rules taking other computations and reconstructing normal forms. We will make a short comparison of Crégut machine, Crégut's KN, and KNV. And with 10 rules of Crégut's KN, our 13 rules is not that much. And Krivin machine realizes call-by-name strategy, and Crégut's Kn, normal order strategy, which is a strong extension of call-by-name. And we would like to investigate if KNV really performs strong call-by-value strategy. So we would like to formalize what strong call-by-value is, and we'll give its reduction semantics. And as an example, we'll define first beta reduction in reduction semantics. We first define beta contraction, which is this rule with substitution, and then we can define beta reduction as a contextual closure of beta contraction to allow it happens anywhere in the term. But this relation is non-deterministic, or it extends whole space of reductions, so we want to restrict contraction rule and reduction contexts to define our strong call-by-value reduction. And the first thing we can read back from obtained machine is that environments contains values which, after decoding, are weak normal forms. This is abstractions or inner terms with symbol Ti. This grammar is similar to grammar of full normal forms and neutral terms, with this only difference that we don't care what happens under lambda in weak normal forms, because weak reduction don't go under lambda. And we can observe that only weak normal forms are substituted in our machine, so we restrict beta contraction to allow only these arguments. The second thing is that stack have this shape invariant, and this shape invariant has not to be guessed. It can be derived from NVE, which uses normal forms and neutral terms explicitly. These constructors get imprinted on stack elements constructors. The stack represents reduction context, but this grammar is written in inside-out manner. So we translate this grammar to finite automaton and we reverse it, so we can read back the grammar of contexts in outside-in manner. And these R contexts represent context of our reduction strategy. And we call this restricted reduction twice right-to-left call-by-value strategy because of two right-to-left choices we've made while modifying an NBE. We prove that it is deterministic and its normal forms are full normal forms, so it is a strong strategy. And moreover, reduction with R context conservatively extends reduction in F contexts, which is right-to-left reduction of fireball calculus studied by Accattoli and Guerrieri. This calculus conservatively extends call-by-value to open terms, so our strategy is also a call-by-value strategy. And fireball calculus has this nice property that all derivations of normal forms has the same length. It is also true for strong call-by-value strategy as an iteration of this strategy, so our twice right-to-left call-by-value strategy is a good representative of strong call-by-value strategies. And finally, we prove that this machine formally traces the strong call-by-value strategy. And to recapitulate, we gave a reduction semantics of strong call-by-value strategy, showed abstract machine tracing this strategy, and this machine is derived through the functional correspondence. Our plan and ongoing work is to eliminate an exponential overhead of execution length, and we believe that functional correspondence will crucially simplify this goal. Thank you for your attention.